Okay, I think that we're going to get started. That's okay. So I think if I stand here, I'm not sure if I'm recorded or not, but welcome everyone. Today, welcome to the CIIR talk. Today's speaker is Parisa Kordjamshidi. Am I getting pretty close there?
Perfect, yeah.
Kordjamshidi. She is an associate professor of computer science and engineering at Michigan State University. She was recently a visiting associate professor at UCLA and is right now a visiting professor at Bloomberg in New York. Her research focuses on natural language processing, multimodal reasoning across vision and language, and neurosymbolic learning. Professor Kordjamshidi, if that does not trip off my tongue yet, received her PhD from KU Leuven, an institution in Belgium that celebrated its 600th anniversary last year. So it was founded in 1425, for those of you who are arithmetically challenged like me, way before anything like universities was happening in the US here. Parisa conducted postdoctoral research at UIUC in Illinois, Urbana-Champaign. She's a recipient of the NSF Career Award, an Amazon Faculty Research Award, and a Fulbright Scholar Award. She currently serves as an associate editor of the Journal of AI Research, a co-editor-in-chief of ARR, an action editor for TACL, and has held roles in organizing committees for a wide range of major conferences. Today, Parisa is going to talk to us about a way to help large language models overcome their deficiencies with spatial intelligence. That's my summary of the talk's content. We're now about to find out what she really means. So please join me in welcoming Parisa to the CIIR talk.
Thank you very much, James, for the kind introduction. And thanks for inviting me, giving the opportunity to talk about our research. So as mentioned, I'm talking about spatial intelligence, specifically neurosymbolic modeling and multiple modalities, here vision and language. So I often start with this example. Many of you might be familiar with this problem that is called visual question answering. And the problem setting as follows. You have a natural language question, like, is the red bike to the right or to the left of Asian people? And then the models are supposed to answer the question given this image. And here human annotation says right. And this is 2019 where this data set was created, and we're probing this to see the challenges of the neural models at the time for vision and language understanding. And the model was perfectly answering this question, which is kind of surprising. It seems a difficult question. But however, when we asked the second question, is the right bike to the left of the Asian people? This is exactly the same kind of question, rephrased, yes, no kind of question answering. And the ground truth accordingly should be no, but the model answers wrongly as yes. So that is the place that we actually doubt if the model really understands objects, their properties, and their spatial relations like left and right and so on. And okay, this is 2019. You might say this is too old. And nowadays, this is customized kind of neural architectures that we were testing. And nowadays, with large vision and language models, we have huge amounts of data fed to these models. And then models already observe all kind of paraphrased questions. And with huge amounts of parameters, they can actually do a better job. So with that argument, I'm going to, like a few years later, I'm going to test DALL-E, which is a multimodal implementation of GPT-3 with 12 billion parameters. This is April 2023, and I'm asking a woman with an apple in her left hand standing to the right of a car to visualize it. And this is, again, we have a spatial relations, we have objects and properties. So you see that the model generates the objects correctly. There is a woman, there is a car, there is an apple, but the spatial relations, like the apple is all the time is in the right hand instead of left hand. And the position of the woman and the car is kind of random. So what do you think if this is still 3 years ago, still old, right? What do you think if I ask this from the state-of-the-art models nowadays, what happens? Do you think this problem is solved, or at least this case will be solved or not? How many people think that?
Nobody's raising their hand here.
Okay, yeah, I can see them. Okay, so that's if you mean to be negative, I think you're correct. So this is kind of 20, like few months back, and this is ChatGPT, GPT-5. It says that it uses GPT-4o for image generation. And you see things has happened, like things are in a better quality. The image of the background, the car, the woman, all look more natural. But the same spatial relation problem, like the apple is in the right hand, the woman actually, the car, the woman stands to the left of the car, not the right of the car. So this is the problem still. So with this introduction, what I'm saying, maybe this is a few months back. Now you tested with another model, I don't know, Nano Banana or something like that. Maybe they get it, I doubt. But still, even if they get it, I want to make this point that, okay, with increase of the data and making models large, we can improve them. But can we feed all possible problems and all possible solutions? So isn't the world dynamic that every day we see new kind of problems happening, and human usually learn compositionally and generalize. We learn basic concepts and we don't need to observe all possible combinations. So that is why I want to argue that large language models suffer from this lack of generalizability and having this basic reasoning skills. And then lack of interpretability. We don't know where they are wrong, why they are wrong, or why they are correct. And we know that with data they improve, but I think this is problematic for like vision and language understanding, though the hype might say, okay, these problems are solved. So now I'm using a lot the term neurosymbolic. I'm going to point to our research and some kind of solutions, but I will refer to neurosymbolic a lot. That's why I wanted to give you a little bit of brief background, what I mean when I mention neurosymbolic. Might be a little bit overloaded term, but here with neural modeling, you know what we mean. We have this maybe customized architecture, neural model, even a perceptron, or large language models. These are neural architectures on the right-hand side. And then we have these symbolic reasoning models like classical AI, like logical reasoning, probabilistic reasoning, Bayesian networks, probabilistic programs. So this is basically symbolic reasoning. And now we want to see like how we can exploit this symbolic reasoning in neural models to deal with these issues of generalizability, interpretability, and all explainability, and all what we discuss as an issue. So here is actually I start to talk about different kind of approaches that we are using to solve this kind of spatial reasoning problems with neurosymbolic modeling. The first problem that I'm going to point to is kind of spatial reasoning over text. When we talk about reasoning, usually we evaluate models with question answering setup. So we ask the model difficult questions and we see, okay, if the model passes them, we say, okay, the model is able to do reasoning. Here is the same story. We try to have a specific type of questions that are asked about like spatial information. Like we have these spatial descriptions, like we have 3 blocks in this image, block A, B, C. Block A is to the left of block B, B is to the left of C, and so on. And then the model needs to answer, is block A to the left of block C? So we can, actually, this is a work that we did a few years back. We created this synthetic benchmark to evaluate LLMs, how they're doing. This is done at the kind of start at the BERT time, BERT-Roberta time of encoder-based models. And then we also had realistic images that we have like this statue with a spread arm on the hill. And we ask, is the statue above the hill or not? So similar to other problems that people were working on, in this problem setting or spatial question answering, we realized, okay, the models can improve if we feed them with more data. Even if we create synthetic data automatically in larger scale, they can improve better. But we actually expect the model some generalizability that, for example, the model needs to know this simple rule, like if left A and B, the model needs to understand right B and A. And this doesn't depend to this synthetic toy environment or this realistic environment. If this is indoor, outdoor, this is a rule that always holds. And we don't want to, it doesn't make sense for us to generate data related to every possible kind of environment for the model to understand this simple rule. Or transitivity, like left A and B, left B and C, left A and C, that is needed for answering this question, is something that we want the model to do, to have a little bit of spatial logic rather than just capturing some clues from training from data. So that is the question that we're asking, how we can train the models to do better generalization in a spatial logic. So again, with the spatial logic, I mean like handful of rules that actually they're generic, they're applicable to any environment, any space, 2D, 3D, like left A and B and right B and A, they are quite qualitative. So the way that we approach this problem, and this is one way of integrating logic or symbolic information into neural model, is as follows. So the problem setting, just to remind you, here the images are just for the sake of explanation. This is pure text-based. We have textual explanation, like there are 3 boxes, white is above orange and red is above white. Now the question is orange below red? This is synthetic data with this environment with nested explanations. And the advantage of synthetic data is that we can have the chain of reasoning to get us from this explanation to the answer to this question. For example, we have like white above orange. We have a handful of these logical rules that says above X and Y, then below Y and X. Then I can say orange is below white. Then I can combine with evidence from the other side and I can apply transitivity and I can come up with this conclusion that yes, the orange is below red. So we have this in the data. This is again, outer is neural modeling, but we try to actually get supervision from this chain of formal logical reasoning to help the models to get the abstraction for the logical reasoning generalization. So what we do is like we start from this data set and we try to get some logical constraints out of this chain of reasoning that we have for every data instance. What is constraint? For example, here we have some consistency constraint that says if this expression like white above orange is correct, then orange below white also should be correct. So basically, these are consistency constraints between the premises and intermediate facts and the final solution that we want to hold here. So if we push the model to be consistent with this logic, we will have such a loss that is kind of includes the task loss. This is just, let's say, cross entropy or whatever that you have for training the model. And then we have this part of the loss that is actually related to violation from these constraints. There is an additional like kind of piece of knowledge that you need to know, and that is the purple part. When we add this loss to the kind of our objective, these logical expressions are not differentiable. That is why we try to actually convert the logic to some soft logic. Instead of and or implication, we have min max or some product. There are different ways to have go from logic, crisp logic to some soft logic. And then we can have that in the our objective that is differentiable. Then we can train or fine tune our model by obtaining supervision from these logical reasoning chains. So as I mentioned, this is actually, at the end, it's a neural model, but the supervision comes from the higher level logical reasoning. Hopefully, it helps the model to make an abstraction beyond the type of object and the type of environment and captures the essence of this logical reasoning that actually is implicit in these rules. So at the end, we don't need these chains. We don't need the formalization. We just have the language model that we can actually use for our usual question answering. So let me point you to some of the results here. So let's talk about this one first. So we wanted to do this because we wanted to answer the problem of like multi-hop complex reasoning. And there was multiple benchmarks created at the time that we were also creating benchmarks. And this one of them was the step game. And you see that we have this K1 to K10. These are number of hops, how many connections you need to make to answer the question. And here is starting from one hop, that is shallow reasoning, to deep 10 hop reasoning. And this is at the time that we were trying smaller models and then encoder-based models like BERT, Roberta, and so on. Some of the results shared here, you see that with this is BERT T Q chain is our model, and we see that we can improve a lot when the depth of reasoning goes higher compared to BERT itself. And also, if we tune with the data, of course, we can get improvement, but still, with the type of supervision that we get, we can obtain more accuracy. And this is compared to also like off-the-shelf language models at the time, large language models, and we saw actually that we could do much better job compared to those models. They were really failing with the multi-hop deep reasoning. In this table, also to just mention a brief takeaway message from this, there are too many numbers here, sorry for that. But here, this is on the realistic data. We have rescue, that is like the statue with the on a hill. And in the realistic data, we didn't see that much of improvement. And the reason is that with the realistic data, we don't have that depth of reasoning. Mostly, we needed common sense knowledge to be used. That's why large models like GPT-4 are already at the time were kind of exceeding all the results. So they were better performing because we just needed common sense, and the model had that. Just to summarize what I explained here, our results based on these experiments and this modeling was that guiding the training through the spatial logic could help nested reasoning compared to usual fine-tuning with just more data. Then logic-based training helped complex reasoning, but actually the GPT family and for the realistic, that more common sense was needed, those models were better. Something that I didn't discuss, and I will point to this later in this talk, is that sometimes the neurosymbolic approaches try to actually, from raw data, get some formal representation and delegate the reasoning to the formal solvers like classical AI models. And in this case, we also had some experiments, and it showed that for the synthetic data, this works good because they are pretty structured, synthetic, and the models can actually map it to formal quickly. But with the realistic data, again, this translation was hard. Though if we had the translation, then the reasoning is solved, but the translation was a bit challenging here. So this is what I wanted to mention about multi-hop nested spatial question answering or spatial reasoning. But when we talk about reasoning or spatial understanding, there are a lot of concepts involved that the language models are lacking. So some of them, this is just kind of complex reasoning. Sometimes even very basic concepts are missing, and that is what I want to talk about next. Some of these missing concepts that we realized was a spatial frame of reference. So here is the example that I showed you, a woman with an apple in her left hand standing to the right of a car. We don't know what is the problem, why the model actually does this wrongly, but something that we think is like perhaps the model doesn't understand the frame of reference. When we say the right of the car, maybe the model just understand is 2D and right is the right of the image. And then if we explain something with respect of an object perspective, then the model doesn't understand it. So now we were thinking maybe we should be explicit about the perspective. A woman with an apple in her left hand standing to the right of a car from the car perspective. So do you think the model will recognize this?
No.
No, okay. You're right. Something happened actually here. The model realized perhaps the car is important, but it dedicated a larger portion of the image to the car, but the spatial understanding still has a problem. So we try to work on this problem because this is, again, very important for situated understanding, 3D environment. When you instruct the robot, go to the left, look at the left of the wall, or look at the left of the person or the building. So that is really important when we want to instruct like agents in the realistic environments. So the work that we did here, we tried to actually a bit structure this problem. Like we looked at, based on kind of this cognitive linguistic studies, we can distinguish 4 types of frame of references. For example, if I have this sentence, a dog is in front of the car, this is, first of all, very ambiguous because it can have different types of frame of references. One of them is external intrinsic. Like here, we mean that the dog actually is outside the car, and so it is also kind of in front with respect to the car. So it's intrinsic and external. So this can be one interpretation here that you see. Another is like external relative. In this image, I think people can see my cursor. So here the dog is in front of the car, but actually the back of the car is in the image. So basically this is with respect to the image, but the dog is still external. And even the dog could be inside the car and in front. So this is totally different. This one may be far-fetched, but the dog is inside, but from the camera perspective is in front. So we're looking at these different cases. We named them like cow case. This is depending on the object properties. Let me also tell you a little bit of the terminology. When we say dog in front of the car, we usually refer to the dog as a locatum or trajector, is the object that we are describing. And then we refer to the car as a landmark or relatum. This is just linguistic kind of term, semantic term. And then we when we actually want to talk about ambiguity in frame of reference, it depends to the properties of the landmark, like the car. If the car has intrinsic direction, then there is ambiguity. If the car has affordance to be container, then there is ambiguity. So we have the car case that has this both, but we have like the cow case that has the direction but is not container, or box case that is symmetric, doesn't have intrinsic direction, but it can be container, and so on. So based on these cases, we try to answer 3 questions. First of all, can LLMs handle this frame of reference understanding? Second, if there is ambiguity in the sentences, what is the interpretation, the bias of the language models for interpreting the frame of reference? And then can we actually help the language models to improve frame of reference understanding? So I just point to some of the work that we did, and to create the first benchmark for this evaluation, we used simple setting with 2 objects involved, locatum and relatum. And then we have like a template that just says a cat is to the right of a dog. And then we actually try to have different types of objects and different types of spatial relations to be covered from the cow case, car case, pen, and box case that I showed you. And then we try to create splits that are ambiguous. We call them A-split, and splits that are clear. When we say clear, it means that the perspective is already in the sentence, so there is no place of ambiguity. When I say a cat is to the right of the dog, from the dog's perspective, I'm clear that you have only one interpretation. So since it is all controlled and synthetic, the interesting aspect of it was that we could use just gaming environments and create the visualization of this. So if I say the cat is to the right of the dog from the dog perspective, I can really just place the things accordingly based on this template in this Unity 3D environment and create the visualization of the scene. Now we have 2 tasks actually based on this data set. The first task is just textual question answering. I have textual explanation, a cat is to the right of the dog from the dog perspective, a dog is facing towards the camera. And then I'm asking questions. Where is the cat from the dog perspective? Or where is the cat from the camera perspective? So we can change the perspective and also test, because we want to test if the models can actually shift perspective and respond correctly. This is one task. It is question answering. But another is just image generation, text to image visualization. If I give you this sentence to the models that are able to do text to image conversion or diffusion, for example, then can they actually follow the perspective? So we have these two test data sets. There are a lot of results. This is a paper that was presented at the EMNL. We actually got SAC award, but then I just shared a few results here. Some of them is like, okay, if first let me explain how to read this table. Sorry for this, a lot of numbers here. The way that we read this table is that first, this is on the ambiguous data set. So the ambiguous split. It means multiple interpretations are correct. So basically we expect the accuracy to be high because if you say left or right, both of them are correct from different perspectives. So the accuracy is not very important here. The important is that when the model is accurate, which perspective they are taking? Do they take relative perspective or intrinsic perspective? And we see actually the models mostly, you see that here, there is a difference between models. For example, if you look at Q12, you see that this is accuracy is high and the model most of the time takes actually relative perspective. So we also saw this is from camera perspective, the sentences. So basically the model, first of all, it is taking relative perspective with respect to the camera. And most of the time actually was correct because whatever mentioned in the context that this something is to the right of something, the answer was accordingly right. Then the model could just use the same lexical form and be correct. So it seemed that the model sometimes just got the clue and the term, spatial term from the context and answered with that and became correct. So it was not very much promising actually. GPT also had the same behavior without chain of thought. But when we did chain of thought, the accuracy sometimes go down, but actually the model does something, changes their mind, and it's kind of 50-50 moving between like relative frame of reference and intrinsic frame of reference. One additional interesting result was that Llama, this is pure text model. So we also try to check the models that are trained with vision and the models are trained with vision and language. And we saw that the models that are pure text, they have less bias towards any perspective, while models that are trained with vision, like we have also in the paper, we have Cohen VL as well, and we see that the bias even becomes more because the models are trained with this just image, internet scale images that are 2D in the wild, and actually most of the time they don't have information about perspective and 3D understanding. So that's why the vision trained models are more biased towards camera perspective. Okay. For the other test also, we had similar results, but also we try to like help this frame of reference understanding to help better diffusion models. Like for example, this was simple prompting approach that if we actually try to make sure that from the text we can, by prompt engineering, we can extract the type of relationships, the type of frame of reference by instructing the model, then we can generate a layout of the image from the text part only. Then we could actually pass the layout to this layout diffusion models. There are certain type of diffusion models that people train them to not only get the textual explanation, but also some layout of bounding boxes of the objects and then generate the image. And since we can control the bounding boxes based on the frame of reference information, we could improve this layout diffusion models. This was another interesting result. But now, okay, to get a pause, I talked about spatial multi-hop reasoning and frame of reference understanding. Now I'm going to talk about something relevant, but a more generic perspective, like how we can use symbolic reasoning for, in general, compositional generalization that is also relevant to spatial understanding, but more generic.
Parisa, can I ask a question?
Sure.
Before you go on to the next section? So the very first example you gave with the red bike and the two women, you don't have to go back to it, but
okay,
also that had a perspective ambiguity, right? Because I looked at it and I thought, oh yeah, that red bike is to their left, but it was on the right in the image, and and the annotation said it was to the right.
Exactly.
So
That is yeah.
I'm
Go
kind of
ahead.
wondering whether that, because there was an assumption in that annotation that could have been dominant at the time, and there could be a lot of training data online that is tricking or training these models from past data to think that the camera perspective is the only thing that matters.
Yes, exactly. That is the point. So that is why the models are trained on this image captioning data, and also like the way that they are annotated is very simplistic, is not 3D, realistic, interactive with agents that are exploring the environment. That's why the data annotation has a problem, and even people didn't think about this. But now that we are making progress, I think we are at the position that now, okay, we have to have better understanding of the space. We need to have 3D understanding because we want agents that actually interactively follow our instructions and navigate in the realistic world. But that is exactly showing, okay, that was from 2019, and now we evaluated frame of reference. We see, okay, it makes sense. The models that are trained with visual data take those data, right? Those are larger scale data available, like ImageNet, I don't know, like VGG, or all these data sets. Sorry, I said VGG, the visual genome, and all these the data sets that are actually don't consider this 3D understanding.
Right. So the second question I have is, is there any interest in dealing with sort of optical illusions for some of these things? I'm thinking of the case where the car was in front of the house or something, and something was on the balcony, and I could imagine creating something where it looked like the car was on the balcony, but as an optical illusion. Or you think about the cases where people are holding up the Leaning Tower of Pisa. I'm not pizza, but Pisa. So it looks like that's what they're doing, but in fact, it's obviously not true. Is that something that is just sort of being ignored right now? I'm just curious.
That is a great question. So we have two things. One is the basic concept. Another is composition of this, and then dealing with the challenge of this composition of all these with the realistic, noisy data. So this experiment, ignorant, the frame of reference experiment was a starting point, and it was ignorant of the complexity of putting things in the realistic domain. It is really a test. If I have two objects, this gaming environment, can they do it? And we see actually this was a challenge. And we just wanted to have this message that we want to make the models to be aware of this concept, and how we can make them to be aware of this concept, to look at the type of relationships and the frame of reference as a thing. But you're right. I mean, if we want to put this in context with everything else, that is still something that nowadays actually people work on this a lot. Nowadays with the embodied AI, actually people look at in the data set creation as well. They look at this 3D understanding, egocentric, and everything is considered. Though those are still kind of more simulated environment and less realistic and less maybe occlusion, and those things are considered still.
Great. Thank you so much.
You're welcome. Thank you for the question. So now this is actually relevant compositional reasoning and language grounding. It's kind of going back to the same example that I started with, like the one that we were just discussing. Here again, visual question answering, and the question is obviously compositional because we are asking how many blue squares are to the left of the large red sphere. We have the objects properties like red, large, and we have the spatial relation. That is why we have this composition of multiple concepts here that needs to be understood. And when we talk about compositional generalization, actually we're caring about novel compositions. If in my training data I have observed a red sphere and a blue square, but I never observed a red square. But in the test time, if I see a red square, I should be able to understand it because these are two orthogonal concepts. And if I understand the concept of color and the shape, then I should be able to understand any combination of the two. This seems very basic, but actually it's surprising to see the models are failing so much. And here is like another data set that are just testing this compositional generalization. This is another case that you say, point to the blue square that is in the same column as the yellow square. And this is the target. The model needs to point to that, a specific point. And surprisingly, in this data set, when we're saying the models that are trained on this, if this blue square doesn't happen in this region, And it happens in other regions, but at the test time, you put it in this region, the model doesn't recognize the blue square, though it saw a lot of them around here. So this is really like looks very dangerous, because the model learns a lot to fit on the data and answer the questions correctly. But then when you give novel compositions, the model doesn't recognize even basic objects. So this is the problem that we want to deal with it. And then this is a framework that actually we build on top of this what's left, that is Josh Tannenbaum and MIT. So the framework is very interesting. I'm just briefly explaining this framework. You have the question, like point to the blue square. You have the image as input. Now, based on these language models, actually nowadays, at least for this kind of compositions that have very clear structure, we can map them with language models to some structure, like point to lambda x, blue x, and square x. You see, this is a probabilistic programming language that is invented by Josh team, and we try to map the query to this formal form. Now, on the image side, we have the perception problem, that I'm going to actually look at this image, maybe process it a bit, and get all the bounding boxes of the objects and pass it to my program. So my program is going to receive 10 bounding boxes, let's say, and then wants to decide if bounding box 1 is blue or not, bounding box 2 is blue or not. And then again, the same bounding box, is it a square or not? So basically, we expect the model to have the concept learners in place. We call it perception module that perceives the concept. And then we put these concept learners in the context of the program, which take care of the explicit composition of this concept. In this way, we don't care if the model doesn't see this composition, because the model just needs to do the basic concept, and we take care of the composition with actual computation in our program. And this program actually can deal with the probabilistic values, because if the model, the perception module says, okay, 80% this square is blue, 20% is not blue, then I can get the probability distribution for blue predicate. Same for the square, 20% square and 90% not. I can get the probability from there. Then I can actually do probabilistic composition that with the soft logical operations. And this is again, and or can be product and sum, or could be max min. So we can actually map this to some soft logic and then compute this in a kind of series of operations that are applied to this and get the answer. Now, when I have the answer, if the answer is like wrong, I can back propagate through this and tune my concept learners. So because all this like pipeline or this computation, forward computation, all is soft and differentiable, I can tune my concept learners. So this is very interesting because, as I mentioned, it can deal with the uncertainty in the concept at the perception level and do the explicit compositional reasoning with explicit probabilistic reasoning in the sense of soft reasoning here, in approximation here, that leads to some generalizability. So now, actually, this is basically a very interesting neurosymbolic framework that separates perception from reasoning, but there are some bottleneck here. One of them is that, okay, when we go to these predicate representations, there is one bottleneck that is whatever I have, okay, it comes from the, is there a blue square in this image? And I get this, the language model tells me you have this blue predicate. But this blue predicate actually needs to have enough instantiations to be trained and give me kind of reasonable probabilities. And if I train the blue and I see another time light blue or turquoise, then that is not observed in my training with my perception module, my model will fail to give me probability of this box being blue or not because it hasn't observed this. So one solution that we did actually to build on top of this, we said, okay, now we get the probability, we get the representation of the visual part, but why we should assume the canonical form of the predicates? We can actually get the distributed representation of the predicates as well. So I can just have the both language and vision part being kind of vector representations, and then I can just get a score by passing both the predicate, linguistic predicate, and the visual part, and get the probability distribution. So I just care about the probability distribution out of this. So I don't care how it comes. I can just use both of them as kind of distributed representations and then or embeddings, and then get the probability score. This actually alleviates this concept bottleneck and training data bottleneck, and we don't lose the similarity between predicates if it exists. And we see that actually our approach, we call it Nessie-Coco model. We have a lot of other components. I just wanted to highlight this major contribution there. It's actually, if we try to perturb the data set with like replacing the terms like cube with box, sphere with ball, and so on, we see the left framework drops a lot, like 49% from 81. But with Nessie-Coco, we have reasonable accuracy. Sometimes there is a drop because, as I mentioned, we assume there is similarity between similar predicates, but it might be the embedding space also is not capturing all the similarities. So this is actually a new extension of this work that is, I'm excited about this, will be presented in CIIR, that we try to alleviate some parts of this, whole framework. One part of it was this probabilistic programming language. We assume that we have a language model that translates questions to probabilistic programs. But actually, if we move to more complex sentences, this becomes more and more difficult. I mean, the language becomes complex or natural, then it becomes more and more difficult. But actually, the language models are good at translating to Python code. That's why we didn't want to stick with the probabilistic programs. We wanted to have a Python translation. That is one big change. But the interesting part is that another change is that we want these concept learners, like BlueX was a perceptron in that framework. But here we can have large language models, specifically large vision and language models here. We can ask natural language questions. I have the concept of a sphere, small blue still. And if I want to say sphere X, what is the score? I'm going to ask the VLM, is this object in this bounding box is a sphere? And I get the probability of yes, no. So I get the probabilities still, this VLM is my scorer, and these Python variables are actually probability distributions. And now I can have the small sphere and a small x and a sphere x combined with this operation, which is my soft logical AND operation, which let's say does the product of the two vectors. So I can have Python implementation of these compositional operations, and I can actually like exploit the for loops, set operations. I can go even beyond first order logic and do second order logic, and flexibility and expressivity of the language increases here. And we can get the same result. And as far as these operations are differentiable, I can backpropagate and tune my scorers and improve my underlying large language models with this pipeline. So this shows actually to be very strong kind of like way of supervising the underlying models. We call it a neuropythonic framework. And we evaluated, I just point briefly, I think I am running out of time, I think. How much time I have? Perhaps I can take a few more minutes, 2 minutes?
Yeah, about 14 minutes.
Okay, sure. Basically, we have this test that is it's called referring expression grounding. You say a man with red shorts and red striped shirt talking to a phone, and the model needs to point to this bounding box that pointing to this specific man. Some of the results on this data set. Okay, this was very interesting. I highlight this because some of the data set, like the one that I showed to you, like visual question answering a standard data set, the language models already have used many of those in their training. So we cannot see the big gap when you do really some contributions to the modeling side. But here with this data set, for some reason, the older models were really performing very bad. Like, for example, interVL 1 billion was doing nothing. None of the groundings were correct. Or with 8 billion, we had 7% grounding correct. Then we tune with the same data we get from, okay, 6% or 1% to 32 by tuning on the same domain of the data. But if we use Neptune framework and we tune the 8 billion, we get to the nearly 70% accuracy. And with the this is just Neptune without tuning. This is Neptune just give me the probabilities and compute the answer is inference time. But if we just tune the smaller model, 1 billion, with this pipeline of this differentiable program, then we can get to the accuracy equivalent to the 8 billion program. This was very impressive result, I think, with this NeuroPythoning framework. So there's no time. I think I want to give time to the questions. So I'm just pointing for the discussion if people want to discuss later. We also work on this spatial language, like vision and language navigation problem. And we follow the similar ideas of decomposition to basic concept and dealing with complexity explicitly. This problem setting is basically you have an agent, this is simulated environment, receives natural language instruction, take right and walk to the kitchen, take left and wait by the dining room table, and so on. The model observes a panoramic images, and then at each time it chooses one of these as a target and goes forward. So the trajectory is a set of these images chosen at each time that the agent moves from one point to another. This is the problem setting, and sorry for this, I don't want to go to the detail, just want to say that for this one as well, we try to come up with some concepts that actually there are skills here, like direction adjustment, vertical movement, go upstairs, landmark detection, go to the bed, or stop and pause operations. So we try to have like separate models that are expert, and then we want to use the language model to order this temporally and then operate as a router that routes us at each stage to the actual expert to do the model. So this is under review, and I think it is archived if you're interested to look at this work. And then one last thing that I wanted to point, I talked about neurosymbolic a lot, and the ways that we can, this image, if you remember in the beginning, we have different ways of interplay between neural and symbolic. And one of the efforts that I have been trying to do over last 5 years was that we wanted to have a generic framework for integration of symbolic reasoning and neural models. We wanted to have a language that actually helps me to express my logic, and then independent from the algorithms, I can use this logic at the training time or at the test time with different types of algorithms. So this is called DomiKnowS. The main idea is that we need both modalities of, if you have heard of this idea of fast thinking and slow thinking, we need to combine both forward computations with searching for best solutions. We need to have various abstractions, concepts, relationships, and their compositions. And that is why we think we need to have like some generic frameworks to support such designs. And DomiKnowS is including, like, it's on top of PyTorch, but we have like a symbolic representation of the named concepts. We have the logical expressions can be written in Python, and we can have different algorithms that can use it. Just to tell you what I mean by algorithms, you remember my spatial constraints with the first part of the talk. We had consistency constraints. We can do them in DomiKnowS. We can use the constraint at the inference time. We can put the constraint in integer linear programming and have the solution subject to the constraints. And we can also do program execution and inference and training, which is also trying to make it in the realistic setup, which is work in progress. The language looks like, okay, concept definition, relation definition, and logical representation. You can just look at the demo that we're having. To end my talk, I just talked about spatial reasoning in complex multi-hop reasoning setups, reasoning over a spatial frame of references, more general language grounding and compositional generalization, getting help from symbolic reasoning. I briefly pointed to this skill-based navigation setup that we're having, and I think it's interesting to really push the community for more generic frameworks for democratizing neurosymbolic modeling. Thank you very much. Also, we have a book actually, and it's not upcoming, it's already published in last December, November. And this work has been done all with my students at the MSU. Thanks them, and thank you for listening. Ready for questions. Thank you.
We have time for a couple of questions. I'll try to find the remote thing.
Hi, I've got a question from online.
Sure.
Okay, you win, go.
Hi, I was wondering if anybody has done this sort of work with satellite imagery where left and right are not so meaningful as maybe north and south. And if this were done in that context, how could this be tied to geospatial directions? And are there data sets or people working on that already?
So actually, I don't know if it has been on the satellite images in the realistic setup, but I have seen people trying to make like this bird eye view also with the synthetic environments and try to deal with this more object-centric relationships. Like you say, okay, to the left of this building, or I don't know, objects that have like this more intrinsic left and right can be mentioned. I think there was kind of not really very matured settings that exist right now. But it's mostly actually situated. The data set that I'm more aware of is like more embodied AI in indoor or outdoor, but situated environments that you actually have the egocentric perspective of the person. And sometimes people try also to look at the like the relative perspective of the other objects that are mentioned. Yeah, there are a lot of works nowadays. The last, I think 1 year has been a lot of new data sets created that they are considering this perspective. Again, repeating myself, I think most of them are in this robotic situated environments for indoor, outdoor. For satellite realistic setting, I'm not sure. Oh, actually, I think like Monash people, they had this DARPA project with this satellite view that was actually trying to have the views from different perspectives and combine it to understand the 3D, to have a 3D understanding. Might be relevant if you're interested. I can send their work to you if you are specifically interested in this, but I'm not sure if they actually address your question specifically, but they started to look at these satellite images.
Yeah, that would be great. I'm typing my email in the chat.
Okay, sure.
Thanks very much.
I can also add a quick note, Michael, that a colleague of us at UMass named Subransu Maji, who's a computer vision faculty at UMass, he has been doing some work with satellite imagery with folks in the astronomy departments. So you may want to also get in touch with them about it.
Sorry, what is his name?
I can write it in the chat.
Do it, please. Thank you.
Okay, I have your email. I'm also sending the link to the my colleagues in Monash also working on this. It was more surveillance actually with DARPA project that they had.
Yes, we have a question here.
So my question is like, usually we have two kind of method to solve a problem. You can have symbolic method, you can have data-driven method. And in the real world, usually like at the end, like a data-driven method will win. So for example, like in the auto self-drive domains, like although like it's very hard to handle the rare situations, but the people still like use the data-driven method anyway. Like they feel like it's more generalized, although it's not very precise and 100% reliable. So do you think in the robotic domain, like how can we make the like a neurosymbolic method like win over the data-driven method in the end?
Actually, this is a great question. I think the way that I think about it is like, okay, there are stages of development of the models, like stages of development of humans. When we learn driving, if I'm like start learning, basically I think a lot. I will be very slow because I need to decide about everything. Is this an obstacle? Should I turn the wheel, or should I? What should I do? I'm doing more symbolic processing and logic. But as I observe a lot of data, then I don't need to think, right? I just do kind of forward computations, perceptive. I do decisions based on my perceptions, and I don't use my reasoning that much, right? So this is happening for the models as well. So if you, for the new concept, like novel compositions, they haven't been observed. It's always neurosymbolic is really important, right? Because you don't have enough data to really deal with that problem or situation with your perception. And then as you get more and more data, you need to just do it quickly. But the main bottleneck here is that when I have to, I mean, for the human, we do is automatically, right? But for models, when we should switch between perception and reasoning is the problem. So I think actually we need both paradigms all the time. But when I should use which depends on how much data I have observed and how much expert or skillful I am about this specific situation. I can just do it perceptive, right? So that is my idea. I don't know if you agree with me or I answered your question.
Yeah, that is a great answer. Thank you.
You're welcome.
So I'll ask a question again. This is James. I'm thinking back to the woman with the apple that was in her right hand rather than her left hand. And so that's a case where it was either ignoring some of the instructions or misunderstanding them. I'm very interested in explanations, and I'm wondering if someone asked the model to describe that image, if it would say that the apple was in the right hand. In other words, does it sort of in some way know that, or does it actually never know that? Because really my question is, can these models who are doing spatial reasoning or some sort of spatial discovery, can they explain what they're doing? Can they say, oh, I'm thinking from the dog's perspective, or I'm thinking from the apple's perspective, or something like that? Or maybe you haven't investigated that, but I'm sort of curious if there's ways for it to explain what it's doing, and if that would help illuminate what's happening.
Yeah, exactly. This is a great point. I think similar to other problems, when we talk about neural models, this is the way that they have been trained to make the connections, basically. This is also kind of neural training. So we are not sure always. I mean, even with GPT, if you ask a question, now it does the line of reasoning for you. It explains why they come up to this conclusion. And it sometimes is actually amazingly and like that it does fallacy and everything looks correct, but actually it's not very logical sometimes. So that's why I think it's kind of dangerous. The models, of course, if we train them with this chain of reasoning, if we have a data set with the data set that we are having, the synthetic part can be verbalized and can be put into the training of the models, right? But then does this reasoning adheres to the actual logic, the chain of thought in language? Does it adhere to the actual formal logic is another problem. And I think there are also some efforts, and I'm also very interested in that direction, that how we can exploit these neurosymbolic approaches to make sure that the reasoning that the models generate adhere to this logical reasoning. And there are a lot of also recent work, like at least a few recent work that they try to, formalize the chain of reasoning, have it verified, and then try to actually make it correct by some verification, and then try to actually reward the model when we are training. So I think those directions are interesting. Like verbalized natural language reasoning chains is helpful, but I don't think it can give us clues, but it's not always, again, reliable as well.
That's fair. Thank you very much.
Yeah, thank you.
I think we're out of time. Obviously, people can look up Parisa on the and send her email messages if you have questions. Thank you very much, Parisa. Thank you, everybody. Please join me and thank our speaker again.
Thank you so much for having me.
We will see you, a couple of us will see you on that other Zoom link that you have access.
Yes, sure. I'm going to move on.
Okay, take care.
Yeah, see you. Bye-bye. Thanks.
大家有点赖啊，还行，把扣拉起来。 有一些写作方面。